All right, for our heat transfer project this semester, we decided to model flow over a heatsink using a Python program and a CFD model. The heatsink we used for our project was a unique one. As you can see here in the picture on the right, it has lots and lots of sort of straight fins, but as you can see, the surface of the interior of these fins are rugged. They have sort of little waves on them to give them more surface area and supposedly to help with convection. It also has another fin cut out in the transflow direction as well. So this is a fairly complicated geometry of this heatsink, and it'd be hard to model this in with simple calculations like we normally can with typical straight pin heatsinks. So for our experiment, we put our heatsink inside the wind tunnel, so we would have a constant air velocity, which came out to be 11.76 miles per hour, and then hooked up some TEC plates to the bottom of the heatsink, which we calculated from other experiments gives about 80% efficiency as a resistance heater. The experiments we ran, we let them go until the heatsink reached steady state, which happened in about seven minutes.
So for part of the modeling was done using a Python programming. With this, in order to use it, it was needed to understand whether this was internal or external convection flow. Since we had a constant influx of power or heat going into the fin array, the flux was constant for the experiment. In order to understand what we had internal or external convection, the boundary layer was compared to the spacing between the fins, and it was found to be about 8 times larger, meaning that the boundary layers did meet and there was internal convection happening. In order to use internal convection correlations, the hydraulic diameter was needed since this was not a cylindrical or circular object within the flow of the air. For this, after finding the hydraulic diameter, the Reynolds number was calculated. In order to understand whether or not this was external or laminar or turbulent flow, the Reynolds number was compared to a value of 2300. If it was less than 2300, we used a constant Newsalt correlation of 8.23, since the ratio of the base to the height of the fin was 78 when it was obtained to be approximately infinity, since it was much larger than 8. For turbulent flow, if it had been the case, the friction and Newsalt correlations would have been found as shown on the slide. After all said and done and Newsalt correlation was determined, the H was found by multiplying by the conduction rate of the fluid divided by, or as shown with the equations on the left, as well as finding the T mean as well. The fin performance values were found using the fin performance equations for the overall efficiency, effectiveness, and resistance, and the results are shown on screen. Taking the calculated results for H and the measured time values, a curve fit was performed to show how H and T were related, and the red line represents the straight line curve fit of the data. And using the line equation, H can be approximated at any point in time to roughly 70%, using the R-squared value as the percentage of accuracy.
For the second stage of our project, we modeled the flow using a CFD solver. CFD stands for Computational Fluid Dynamics, and the CFD model creates a mesh of the fluid that flows over any object, in this case a heat sink. That fluid is then broke up into small elements and calculations done for each element. This is very similar to an FEA analysis, except the medium is a fluid and most of the time is moving. The specific software I used is called OpenFoam, which is an open source Linux-based software. There's a bit of learning curve for this software, but let's say it's free and nonetheless very versatile. It can handle many types of flows and fluids, and can solve for things such as velocity in different directions, pressure, and temperature, among other things. For our specific model, you can see here, we modeled the flow over the space between just two of the fins, since the fins were repetitive throughout the thing, and we wanted to simplify our model. So you can see, as you can see, the red part there is the actual fin, and the blue just is the air that goes around it. So the specific way we solved for the convection with the CFD model was getting the change in temperature at the boundary layer of the heatsink. So at the heatsink surface, it's obviously going to be very hot, and as you move away from that, it's going to cool down. Now, if we look at that at the very small level, like half a millimeter, we can actually determine the heat transfer coefficient from that. So taking an average over these 5 spots, because this model includes millions of cells, and we didn't want to do the calculations for all of them. We just took an average over a general space of the heatsink. And doing this, we got using this equation on the top right, we got a heat convection coefficient of 45.357 watts per meter squared Kelvin. Sorry.
As can be seen, these are two very different methods of finding the heat transfer coefficient of the fin array. For Python, experimental data, the geometry of the fin, and the thermophysical properties of the air at the local pressure are of high importance. As the data was time-based, the average was found by averaging all the ages for the experiment. In all, it took about 3 to 4 hours to come up with the coding using the equations and the data.
The open foam CFD solution in comparison underestimated the heat transfer coefficient. However, it did not rely on experimental data, but only relied on the geometry and properties, external properties such as velocity and power alone. The specific solution only solved for a steady state convection rate. And all in all, it took about 7 to 8 hours from start to finish to make. Comparing these two methods, we can see that while the open foam solution could, in theory, solve for a lot more than just the convection coefficient, for the specific problem, Python was probably best in terms of accuracy and time.